Both the pictures of the bubbles and the streamline's vorticity, as well as the graph that I showed you on the last slide of the entropy versus drag, suggest strongly that the reduction for drag reduction for the case of a deformable bubble has to do with the deformable bubbles somehow reducing the streamline's vorticity. The question obviously is how. We have looked at a number of pictures or plots of the flow to try to elucidate the mechanisms, and the mechanism sketched out in this slide here is sort of the best we have come up with so far. If you look at idealized hairpin vortex, and bear with me if my artistic abilities are somewhat limited, you have a vortex that is, forms a U-shape downward that's lifted a little bit up from the wall at the end, but the vorticity induced by the legs of the hairpin have to be matched by wall-bound vorticity of the opposite circulation that's bound to the wall to kill the velocity and bring it down to zero at the wall. As the bubbles move over the hairpin, the deformable bubbles move over the hairpin, we believe that the bubble squeezes the hairpin down toward the wall, and now you have vorticity of one sign being pushed into vorticity of the opposite sign, and we believe that that leads to mutual cancellation. On the right-hand side of the slide, I've tried to plot a cross-section where the wall-bound vorticity is shown and below the legs of the vortex. Obviously, for this mechanism to be effective, the bubbles really have to be of the order of the separation between the vortices, and that's why we believe that the bubbles have to be reasonably large for this mechanism to work. We also believe that they have to be deformable so they can slide over the vortices and push them toward the wall. So we think we understand why the deformable bubble caused drag reduction. The bubbles slide over the hairpin vortices next to the wall, force them into the wall or toward the wall, and the vorticity cancels. But why do the spherical bubble cause drag increase? In order to try to understand that a little bit better, we have plotted in this picture the average fluid velocity and then the velocity of the bubbles. It's clear that for the most part the bubbles move with the fluid just as you would expect, because after all there is no buoyancy along the wall. However, very close to the wall, particularly for the less deformable bubbles, the bubbles lack the flow field. The reduction in the velocity of the nearly spherical bubble or less deformable bubbles versus the more deformable ones is shown perhaps a little bit better in this graph, where we have calculated the average difference between the velocity of the bubbles and the velocity of the fluid at that location for all the bubbles at several different times. The circles are actually the times when we have calculated the lag velocity, and then we have fitted a smooth curve through those points. Even though the more deformable bubbles lag the fluid a little bit for essentially all times, it's clear that the less deformable bubbles lag considerably more. The less deformable bubbles are generally closer to the wall than the more deformable ones. In this particular graph here, we have plotted the deformation of a bubble versus the distance from the wall. Once all the bubbles are sufficiently far from the wall, for the most part they are nearly spherical and there's a relatively small deformation. And as all the bubbles are very close to the wall, or those bubbles who are very close to the wall can obviously be deformed strongly. However, if you look very carefully, and my apology for this somewhat messy graph, we will see that the more deformable bubbles are generally further away from the wall than the less deformable ones. To try to understand a little bit better how the bubbles act on the fluid, we've tried to estimate the force between the bubbles and the fluid by replacing the bubbles essentially by a force field that gives exactly the same flow field as the bubbles do. We have then averaged over planes parallel to the wall to try to estimate the average force from the bubbles on the fluid. In this particular graph, we plot the force distribution at a single instant in time, and that's why it's sort of a little bit wiggly, for both the most deformable bubbles and the least deformable bubbles. The most deformable bubbles, essentially there is essentially no force between the bubbles and the fluid. The bubbles simply move with the fluid velocity, and because there is no relative slip, there is essentially no force between the bubbles and the fluid. For the deformable bubbles, this is true in the middle of the domain, but when you get closer to the wall, you see that very close to the wall there's a positive force, because the bubbles move faster than the fluid. They will drag the fluid with them, push the fluid to go faster. But a little bit further away from the wall, the bubbles move slower than the fluid there, and therefore the bubbles slow down the flow. And it's this slowing down the flow, moving slower than the average fluid velocity, that causes the drag by the nearly spherical bubbles or the less deformable bubbles. So overall, we believe that the reason that these nearly spherical bubbles or the less deformable bubbles increase the drag is because they are less deformed. They therefore stick into the viscous sublayer closer, so they are slowed down, and because they're slowed down, they are essentially offer a resistance to the fluid motion, and that's what leads to a larger drag. So it's a little bit like spheres being glued to the wall, except of course they're not completely glued to the wall because they do move along the wall, but not as fast as the fluid. So we think we understand reasonably well why the more deformable bubbles cause drag reduction and why the less deformable bubbles can cause drag increase. Obviously, for the bubbles to have effect on the flow, they have to be in the right place at the right time. And the right place is very close to the wall. To see how the bubbles move in the turbulent flow, we have in this figure plotted the path of the bubble in the plane perpendicular to the flow at several times. So we follow the path from their initial location, very near the wall, that's what we have marked by red dots, throughout time. Obviously, the bubbles are dispersed away from the wall, but just as they are dispersed away, some of them come back to the wall again. If we look very carefully at the graph, we will indeed see that the more deformable bubbles are dispersed more, and many of the nearly spherical bubbles or less deformable bubbles actually stick close to the wall for a very long time. This is the path of the bubbles again, but now we have plotted them in a plane formed by the wall normal direction and the streamwise direction. So we're looking in the spanwise direction. Again, we see that the more deformable bubbles disperse away from the wall relatively quickly. Indeed, we see that at the top wall, we actually have all the bubbles having left at the latest time. Indeed, if we recall back to the plot of drag versus time, at that time the wall drag on the top wall actually started to increase again. For the less deformable bubbles, we see again, as we saw in the previous slide, that the bubbles tend to stick to the wall much longer than they do for the more deformable ones, even though there are obviously some bubbles that make it into the interior of the domain. And this again is another way of looking at the dispersion of the bubbles. Here we have plotted the void fraction averaged over planes parallel to the wall at several different times. This is a little bit confusing graph and you have to study it rather carefully, but it shows again that the less deformable bubble disperse more rapidly from the wall than the more spherical ones. Okay? So basically, you will find a large hump remaining at the late time for the nearly spherical bubbles, which you don't do for the more deformable ones. In the simulation presented here, we do not allow the bubbles to coalesce. In reality, of course, it is possible that if the bubbles come close and stay close enough for the film between them to drain, they could coalesce. To examine whether that's possible or what the likelihood of bubble coalescence is, we have monitored the distance between the bubble centers, and when the bubble centers are close on about a diameter and a little bit more, usually taking about 5% of the diameter, we mark them, the bubble pair, as close. In the graph we show how many bubble pairs are close at any given time, and it's clear that the less deformable bubbles, the spherical ones, actually at most there is about one bubble pair that is close at any given time, but the more deformable ones, there are actually a larger number of pairs that are close by the definition we use here. However, the deformable bubbles actually, because they are deformed, they can be their centroids can be about a diameter apart without their surfaces actually being that close. In any case, it is clear that the possibility of bubble coalescence should be considered